let's say you have an initial condition x0 and you calculate the orbit of that initial condition under the map F. And then you calculate the Lyapunov number of that orbit and you end up with a number L. The question now is, if you consider not the map F, but the map F applied k times, what is then the Lyapunov number of the orbit of x0? So pause the video and see if you can figure out what the correct answer is. Let's start by writing down the Lyapunov number of the map just applied once. So what we need to do here is look at the orbit of our initial condition x0 under the map F. So the map only applied once at a time. So we'll start at initial condition x0. If we apply the map once, we have x1 and then x2, x3, x4. So let's say we keep going until we have n total number of terms in this series here. So then we have xn minus 2, and then the last one is xn minus 1. And since we start at x0, this basically gives us here n number of points that we consider in our orbit. To calculate the Lyapunov number, what we basically need to look at first is the geometrical average of the magnitude of the derivative of all of these points. So we're going to look at the geometrical average of, for example, f prime x0 in magnitudes and so on, and then f prime of x n minus 1. Now, in order to calculate the geometrical average, we need to multiply those terms, those factors rather, and then we need to raise them to the power of 1 over the total number of things that we average geometrically. So here we have n things that we average, so we should raise that to the power of 1 over n. And if we then take the limits of n going towards infinity, that will give us our Lyapunov number L. Okay, so that's just a quick recap of the definition of Lyapunov number for the regular map. Now, what we're really after is the same thing, but for the map F applied twice. So now we're going to look at the orbit of the same initial condition, this time under the map F applied twice. And in general, we're going to look at F applied n times, but just to make our life a bit easier notation-wise, we're going to focus on the map F applied twice. Generalization is trivial. So now we start at x0, and then the first thing we hit is not x1. We skip that because we applied the map twice, and then we end up at x2, and then the next one is x4, and then the final one in our case is going to be xn minus 2. Now, without loss of generality, we're going to say that this n here that we considered was an even number. So in this case, how many points do we have here? So we have the same number of points here, but we always skip the odd one that's coming after it. So basically, in our case now, we have n over 2 points in our orbit. And that's going to be relevant if we calculate the Lyapunov number of this compound map. So we call that L2, let's say. Now for that Lyapunov number, again, we need to look at a geometrical average of derivatives. So what's happening in this case? The first derivative is the derivative of the map F applied twice, obviously, at the point x0. And then we have the derivative of the map F applied twice at the point x2. And then we end at the derivative F twice xn minus 2. Okay, so these are the objects of which we need to take the geometrical average. How do we do that? We multiply them all together and we raise them to the power 1 over the number of things that we average, which is in the second case now n over 2. So we raise that to the power of 1 over n over 2. And again, in the limits of the number of things that we average going towards infinity, this will give us the Lyapunov number of the second map. Now the important part is to try and relate what we have between curly brackets here to what we have between curly brackets there. And this might be a good time to pause and see if you can rewrite the stuff that you have here to more closely resemble what you had up there. So this is something we also did when we were looking at the stability of periodic points, periodic orbits. So let's see what happens if you want to calculate the derivative. So let's say the first term here. So if we have the derivative of the map f applied twice, that's basically the derivative of f of x0. So in that thing, I'm going to take the derivative of. So now we can just look at our chain rule. The chain rule will tell us that this is f prime of f of x0 times f prime of x0. And we know that f of x0 is x1. So basically, knowing this, we can write this thing here as f prime x0, f prime x1. And then for the next thing, we're going to write f prime x2, f prime x3. And we can keep on playing that game. And then the conclusion basically is that the stuff between curly brackets here and the stuff between curly brackets there is exactly the same. And that will help us to draw our conclusion because we know that the Lyapunov number of the original map, that's basically the limit of the number of terms going towards infinity, of the stuff between curly brackets, which we're going to call A. So let's have a look at the formula. So the stuff between curly brackets is raised to the power 1 over n. So that's the definition of our first Lyapunov number. The Lyapunov number of the compound map is, again, the limit of the same stuff between curly brackets, but this time we raise it to the power 1 over n over 2. So that's raised to the power 2 over n. So here we can clearly see that the Lyapunov number of the compound map is just the square of the original Lyapunov number. And if you come to think about it, that actually makes a lot of sense, because what is the Lyapunov number? The Lyapunov number tells you on average, if you have a certain orbit, how much divergence is going on when you take a single step here. Now, if you only take a single step and you say that that divergence is roughly changing with a factor of L, if you take 2 steps in succession, then obviously the divergence for these 2 steps taken together is going to be L times L. So it makes a lot of sense, and here we've also made it explicitly by looking at the formulas.